To address electrical shocks in an ungrounded delta system, a systematic approach is necessary. Prior to visiting the job site, several steps can be taken to gather information and prepare for the investigation. Firstly, it is essential to review the electrical equipment information. Obtain documentation or specifications for the equipment, including the manufacturer, model number, and voltage rating. This information will provide a baseline for understanding the equipment's intended operation and safety features. Secondly, check the grounding and bonding of the equipment. Ensure that the equipment is properly grounded and bonded, verifying that all electrical panels and enclosures are grounded. Check that there are no open connections or damaged grounding conductors. Proper grounding is critical for safety as it provides a low impedance path for fault currents, helping to prevent electrical shocks. Thirdly, inspect the wiring connections to and from the equipment. Pay attention to any loose connections or insulation damage. Verify that all wires are properly sized and rated for the current draw of the equipment. Undersized or damaged wiring can lead to overheating and electrical hazards. Fourthly, test for shorts to ground on the equipment. Use a multimeter to test for any shorts to ground. Disconnect any ungrounded conductors before performing this test. A short to ground can indicate a fault in the equipment that could cause electrical shocks. Fifthly, check the circuit protection devices protecting the equipment. Ensure that the circuit breakers or fuses are properly sized and functioning correctly. Verify that the trip settings are appropriate for the load. Properly sized and functioning circuit protection devices will help to prevent overloads and short circuits, reducing the risk of electrical hazards. Sixthly, review the maintenance history of the equipment. Obtain any maintenance records to identify any prior issues or repairs that may be related to electrical safety. Past issues can provide valuable insights into potential problems. Seventhly, contact the equipment manufacturer for technical assistance and guidance, if possible. They may have specific recommendations for troubleshooting and resolving electrical issues. Manufacturer assistance can be invaluable in complex situations. When dealing with ungrounded delta systems, additional considerations are important. Verify that the equipment is not inadvertently grounded through any other paths, such as through connecting cords or shared grounding with other systems. Accidental grounding can create unintended current paths and increase the risk of electrical shock. Ensure that employees are using appropriate personal protective equipment, such as insulated gloves and shoes. Personal protective equipment provides an additional layer of protection against electrical hazards. Implement safe work practices and training for employees to minimize the risk of electrical shock. Training and safe work practices are essential for preventing accidents and injuries. Consider the use of a ground fault circuit interrupter, or GFCI, as an additional safety measure. A GFCI can detect small ground faults and quickly de-energize the circuit, reducing the risk of electrical shock. To elaborate on grounding and bonding, it is crucial to understand their specific roles in electrical safety. Grounding provides a path for fault currents to flow back to the source, allowing the circuit protection devices to trip and to energize the circuit. Bonding connects all metallic parts of the electrical system together, ensuring that they are at the same potential. This reduces the risk of electric shock if someone comes into contact with two different metallic parts. When inspecting wiring, pay close attention to the condition of the insulation. Damaged insulation can expose live conductors and create a shock hazard. Look for signs of cracking, fraying, or melting. Also, ensure that all wire connections are tight and secure. Loose connections can cause arcing and overheating. When testing for shorts to ground, use a multimeter set to the resistance setting, or ohms. Connect one lead of the multimeter to a known good ground, such as a grounding electrode or a grounded metal enclosure. Then touch the other lead to various points on the equipment, such as the metal frame, the motor housing, and the control panel. If the multimeter reads a low resistance, such as a few ohms or less, it indicates a short to ground. When checking circuit protection devices, make sure that they are the correct type and size for the equipment. Circuit breakers should be properly rated for the current draw of the equipment, and fuses should be the correct amp rating. Also, verify that the circuit breakers are tripping properly when tested. You can use a circuit breaker tester to simulate an overload or short circuit and verify that the breaker trips quickly and reliably. When reviewing maintenance history, look for any recurring problems with the equipment. Has the equipment experienced frequent electrical failures or breakdowns? Have there been any reports of electrical shocks or near misses? Identifying recurring problems can help you to pinpoint the underlying cause of the issue. When contacting the equipment manufacturer, be prepared to provide them with detailed information about the equipment and the problem you are experiencing. The more information you can provide, the better able they will be to assist you. They may be able to offer specific troubleshooting steps or recommend replacement parts. In ungrounded delta systems, it is particularly important to be aware of the potential for floating voltages. In a grounded system, the voltage between each phase and ground is fixed. However, in an ungrounded system, the voltage between each phase and ground can vary depending on the impedance of the system. This can make it difficult to detect ground faults. One way to address this issue is to use a ground detection system. A ground detection system monitors the voltage between each phase and ground and provides an alarm if the voltage exceeds a certain threshold. This can alert you to the presence of a ground fault before it causes a shock. Another important consideration in ungrounded delta systems is the potential for transient overvoltages. Transient overvoltages are brief spikes in voltage that can occur due to switching operations or lightning strikes. These overvoltages can damage equipment and create a shock hazard. To protect against transient overvoltages, you can use surge protection devices, or SPDs. SPD are designed to divert transient overvoltages to ground, protecting the equipment from damage. When implementing safe work practices, it is important to emphasize the importance of the energizing equipment before working on it. Always disconnect the power supply before performing any maintenance or repairs. Use a voltage tester to verify that the equipment is de-energized before touching any electrical components. Also, be sure to use lockout-tagout procedures to prevent the equipment from being accidentally re-energized while you are working on it. In addition to insulated gloves and shoes, other types of personal protective equipment may be necessary depending on the specific task. For example, if you are working on overhead power lines, you should wear a hard hat and safety glasses. If you are working in a confined space, you should wear a respirator. Always consult with a qualified safety professional to determine the appropriate personal protective equipment for the task. When considering the use of a GFCI, it is important to understand that GFCIs are designed to protect people from electrical shock, not to protect equipment from damage. GFCIs detect small ground faults and quickly de-energize the circuit, preventing a shock. However, they may not prevent damage to equipment caused by larger ground faults or short circuits. Therefore, it is important to use GFCIs in conjunction with other circuit protection devices, such as circuit breakers and fuses. In addition to the steps outlined above, it is also important to regularly inspect the electrical system for any signs of damage or deterioration. Look for cracked or damaged insulation, loose connections, and corroded components. Addressing these issues promptly can help to prevent electrical hazards. Also, be sure to keep the electrical system clean and dry. Dust, dirt, and moisture can all contribute to electrical problems. Finally, it is important to remember that electrical work should only be performed by qualified and trained personnel. Working with electricity can be dangerous, and it is important to have the knowledge and skills necessary to do the job safely. If you are not qualified to perform electrical work, hire a licensed electrician to do the job for you. When documenting the electrical equipment information, be sure to include not only the manufacturer, model number, and voltage ratings, but also the serial number, date of manufacture, and any other relevant information. This information can be helpful in identifying the equipment and obtaining replacement parts. When checking grounding and bonding, be sure to verify that the grounding conductors are properly sized according to the National Electrical Code, or NEC. Table 250.122 provides the minimum size of grounding conductors for various circuit ampacities. Also, be sure to verify that the grounding electrode system is properly installed and maintained. The grounding electrode system consists of one or more grounding electrodes, such as ground rods, ground plates, or underground metal water pipes that are connected to the grounding conductor. The grounding electrode system provides a path for fault currents to flow to ground. When inspecting wiring, pay particular attention to the condition of the wire insulation. Look for any signs of cracking, fraying, or melting. These are all signs that the insulation has been damaged and needs to be replaced. Also, be sure to check the wire connections for tightness. Loose connections can cause arcing and overheating, which can lead to electrical fires. When testing for shorts to ground, be sure to disconnect the power supply before performing the test. This will prevent you from getting an electric shock. Also, be sure to use a multimeter that is properly rated for the voltage you are testing. Using an improperly rated multimeter can be dangerous. When checking circuit protection devices, be sure to verify that the circuit breakers and fuses are properly sized for the load. Oversized circuit protection devices will not protect the equipment from damage, and undersized circuit protection devices will trip unnecessarily. Also, be sure to verify that the circuit breakers are tripping properly when tested. You can use a circuit breaker tester to simulate an overload or short circuit and verify that the breaker trips quickly and reliably. When reviewing maintenance history, look for any patterns of electrical problems. Has the equipment experienced frequent electrical failures or breakdowns? Have there been any reports of electrical shocks or near misses? Identifying patterns can help you to pinpoint the underlying cause of the problem. When contacting the equipment manufacturer, be prepared to provide them with as much information as possible about the equipment and the problem you are experiencing. The more information you can provide, the better able they will be to assist you. Be sure to include the manufacturer, model number, serial number, date of manufacture, and a detailed description of the problem. In ungrounded delta systems, it is important to be aware of the potential for capacitive coupling. Capacitive coupling occurs when two conductors are located close to each other and are separated by an insulator, such as air or insulation. This creates a capacitor, which can store electrical energy. If one of the conductors is energized and the other is grounded, a current can flow through the capacitor. This current can be large enough to cause an electric shock. To reduce the risk of capacitive coupling, keep conductors as far apart as possible and use shielded cables. Also, be sure to ground all metal enclosures. When implementing safe work practices, it is important to follow all applicable safety regulations. In the United States, the Occupational Safety and Health Administration, or OSHA, sets the safety standards for electrical work. Be sure to comply with all OSHA regulations. Also, be sure to follow any safety procedures that are specific to the equipment you are working on. When selecting personal protective equipment, be sure to choose equipment that is appropriate for the task. Insulated gloves should be rated for the voltage you are working on. Safety glasses should be impact resistant, and hard hat should be ANSI approved. When considering the use of a GFCI, be sure to install it in a location where it will be easily accessible. Also, be sure to test the GFCI regularly to ensure that it is working properly. You can test a GFCI by pressing the test button. If the GFCI trips, it is working properly. If it does not trip, it needs to be replaced. In addition to the safety measures outlined above, it is also important to train employees on the hazards of electricity and how to work safely around electrical equipment. Employees should be trained on the proper use of personal protective equipment, lockout-tagout procedures, and other safety procedures. They should also be trained on how to recognize and respond to electrical hazards. By taking these steps, you can help to prevent electrical shocks and injuries in the workplace. When dealing with electrical equipment connected to a three-phase power transformer without an axial or neutral tap, resulting in an ungrounded delta system, the absence of a neutral presents unique challenges. Firstly, confirm with certainty that there is indeed no neutral connection available from the transformer. An electrician's assessment is a good start, but double-checking the transformer's nameplate and internal wiring diagram is crucial. Misidentification can lead to incorrect assumptions and troubleshooting strategies. Secondly, understand the inherent characteristics of an ungrounded delta system. Unlike grounded systems where a fault to ground creates a direct path for current, an ungrounded delta system allows a single ground fault to occur without immediately tripping a circuit breaker. This is because the fault current is limited by the system's capacitance to ground. However, this does not mean the system is safe. A second ground fault on a different phase will create a phase-to-phase fault, resulting in a high fault current and potential for severe damage and shock hazard. Thirdly, investigate the possibility of a floating neutral. While the transformer itself may not have a neutral tap, certain loads connected to the system, particularly those with single-phase components, can inadvertently create a neutral point through unbalanced impedances. This floating neutral can then become a source of voltage fluctuations and contribute to shock potential. Check for any unintentional neutral connections or unbalanced loading across the phases. Fourthly, consider the presence of static electricity. Ungrounded systems are more susceptible to static buildup, especially in dry environments or with equipment that generates friction. Ensure proper grounding and bonding of all equipment, including enclosures, frames, and even moving parts. Static dissipative mats and wrist straps can also help minimize static discharge. Fifthly, check for harmonics. Nonlinear loads such as variable frequency drives, electronic ballasts, and computer power supplies can introduce harmonic currents into the system. These harmonics can distort the voltage waveform and increase the risk of equipment malfunction and shock. Consider using harmonic filters to mitigate these effects. Sixthly, use a high-impedance ground detector. Since standard ground fault protection devices may not work effectively on an ungrounded delta system, a high-impedance ground detector can be used to monitor the system for ground faults. This device injects a small DC voltage into the system and measures the current flow to ground. If a ground fault occurs, the current will increase, triggering an alarm. Seventhly, consider converting the system to a grounded configuration. If feasible, converting the ungrounded delta system to a grounded Y system can significantly improve safety and reliability. This involves installing a grounding transformer, such as a zigzag transformer or a Y delta transformer, to create a neutral point and provide a path for ground fault currents. However, this conversion may require significant modifications to the electrical system and careful consideration of the load requirements. Eighthly, ensure proper insulation coordination. The insulation of all equipment and wiring must be adequate for the system voltage and any potential overvoltages. Inspect for any signs of insulation damage or deterioration. Also, consider using surge protection devices, or SPDs, to protect against voltage transients caused by switching or lightning strikes. Ninthly, implement a robust safety program. Train employees on the hazards of ungrounded delta systems and the importance of proper grounding and bonding. Provide them with appropriate personal protective equipment, such as insulated gloves and shoes. Establish clear procedures for reporting and investigating electrical incidents. Tenthly, perform regular inspections and maintenance. Schedule regular inspections of the electrical system to identify and correct any potential problems. This includes checking for loose connections, damaged wiring, and corroded components. Also, perform regular testing of grounding and bonding connections to ensure their integrity.